This is the pre-lab talk for experiment number 9 for Chem 120, Thermodynamics and the Solubility of KHT. The goals for this experiment are to experimentally determine the solubility product constant for potassium hydrogen tartrate, or KHT for short, at various temperatures. We will use these KSP values to calculate the change in Gibbs free energy for the dissolving of KHT at different temperatures. We will then plot these delta G values as a function of temperature to experimentally determine the delta S and delta H, or the entropy and enthalpy changes for the dissolving of KHT in water. We will also take a look at how the addition of a strong base or a compound with a common ion to KHT will affect its solubility. In today's safety pause, we note that potassium hydroxide and sodium hydroxide solutions at a 1 molar concentration are moderately corrosive, and special care should be used when handling them. We also note a little bit of hot plate safety. In this experiment, we'll be using a warm hot plate to warm up our solution of KHT in pure water. We want to make sure that we keep the warm hot plate to the rear of the hood so that it's to reduce the risk of the hot plate being tipped over, causing a scalding injury. And we also want to make sure that we keep all wires, namely the wires from the temperature sensor and the LabQuest Mini, away from the warm hot plate. We also want to let the hot plates cool down before putting them away in the designated cabinets. And as always, we want to make sure that we goggle it and wear our flame-resistant lab coats. Let's take a look at some important concepts that are related to this experiment. The first concept that's important is looking at solubility equilibrium. I can write an equilibrium between solid potassium hydrogen tartrate and the aqueous ions in solution, potassium and the hydrogen tartrate ion, or HT- for short. When this system reaches equilibrium, the product between the potassium and hydrogen tartrate ions concentrations equal a constant. We call this constant this solubility product constant, or the KSP. We note that the ion product is only a constant once the solution is saturated, which implies that both solid and the aqueous ions must be present. KSP can be related to the Gibbs free energy change for this process using the equation delta G is equal to minus RT natural log of KSP, where R is equal to 8.314 joules per mole times Kelvin. Note that your units will be joules per mole for delta G, and T is your temperature in Kelvin. The Gibbs free energy change tells us about the spontaneity of a process. Processes or reactions with a negative delta G are spontaneous or occur as written without work being done on the system. If delta G is positive, then that means that the reaction is non-spontaneous. Delta G depends on several factors, namely the temperature and two other thermodynamic properties, the entropy change, delta S, and the enthalpy change, which is delta H. All of these factors are combined in the equation delta G is equal to delta H minus T delta S. You can see from this equation that the interplay between the enthalpy change and the entropy change can help determine whether or not delta G is positive or negative, or if your process is spontaneous or non-spontaneous. The favored signs for delta H and delta S are that delta H is negative, meaning stronger bonds are formed and the energy of your system is lowered, and delta S being positive, meaning you're increasing the number of states available to the system according to the second law of thermodynamics. If delta H is negative and delta S is positive, then delta G will be negative, and the reaction or process will be spontaneous at all temperatures. If the opposite is true, if delta H is positive and delta S is negative, then a reaction will be non-spontaneous at all temperatures. The real fun comes when delta H and delta S have the same sign. Then it becomes temperature dependent whether or not the reaction is spontaneous or non-spontaneous. When both delta H and delta S are negative, then you have an enthalpy-driven reaction, where the reaction is driven mainly by the lowering of the energy of the system by forming stronger bonds and interactions. This type of reaction is spontaneous at low temperatures, but non-spontaneous at relatively high temperatures. You can also have reactions that are entropy-driven, that is, are driven by the increase in the number of states available to your system. This occurs when both delta S and delta H are positive. These type of reactions tend to be non-spontaneous at low temperatures, but spontaneous at high temperatures. In this experiment, since we are determining delta G at different temperatures, we can plot delta G as a function of the Kelvin temperature. Our data can be fit to a linear function that has a slope of negative delta S and an y-intercept of delta H. Therefore, in this experiment, we'll be able to determine not only the KSPs at different temperatures, but several thermodynamic properties. Notice that delta S and delta H are not temperature dependent, at least not at the temperature range we are studying. However, delta G is. Let's take a look at a few procedural points. We note that we'll perform one trial of this experiment of part 1 to show you how we collect the data that you'll be given to analyze. It is important to note, especially as you do calculations, to be mindful of the precision of our different measurements. We want to achieve some high quality results. Therefore, we use our analytical balance to determine the mass of KHT, and we also use a burette to deliver our water volumes. Therefore, when you're doing your calculations, it's very important that your molar mass at least have 4 sig figs, so you do not limit the precision of your calculations. And as always, you should carry sig figs through your calculations based on the numbers that you start with. As mentioned before, it is important to be very careful with hot plates. In this experiment, two hot plates will be used. One hot plate will be used for heating up the solution, and a second hot plate will be used as a stirrer only, to be used for cooling down your substance. Another important aspect of this experiment, as you'll see in the lab video, is looking for the first hint of a precipitate. We note that our ion product, the product of potassium and hydrogen tartrate concentrations, is equal to KSP at a given temperature if you have a saturated solution. As mentioned in your lab notebook, or in your lab introduction, it is important that we look for the first hint of precipitation formation. This is at the beginning of the formation of our saturated solution, where we can know our concentrations of potassium and hydrogen tartrate ions. if we wait too long, then our concentrations will become unknown. Here's a video that shows that process. This is a solution that has the KHT dissolved in water. There is a stir bar and a black piece of paper in the background. Remember, we are looking at the first hint of cloudiness, as I can see right about now. This is very difficult to look for, and usually when we do this lab, one lab partner is watching the solution while the other lab partner is manning the computer. Now it is very obvious that a precipitate has formed. At this stage, it's kind of too late, which is why it's important to be very attentive to the solution. You can practice this as you look at the trial. You'll notice that I sort of have a hard time with this. It's better with two people. Here are some extra hints for the analysis. Sometimes students struggle with the calculation of KSP. You'll get some practice of this in your pre-lab. However, it's important to note that to calculate the KSP, you need to essentially square the concentration of KHT. Since you want to note that for every 1 mole of KHT formed, you get 1 mole of potassium ions and 1 mole of HT ions. The only difference in each trial is that the volume of water changes as 10 milliliters are added to the flask for each run. It is also important for you to make your delta G versus temperature plot in a very nice way. As a reminder, you want to make sure that you use Microsoft Excel to do your plotting. You want to make sure that as you make your plot, you choose a nice scale for your plot so that the line takes up most of the space of the page as the plot shown on the right. And you want to make sure that your axes are labeled and you include a title. You also want to make sure that you add major and minor grid lines. Another important point of this lab is to remember that the slope of this line is negative delta S. This means that the delta S, in this case, should be greater than 0. Okay, I hope you have fun analyzing all the data.